Hey folks, it's Friday, April 17th, and we're going to finish off the week doing a little bit of an introduction to electromagnetic radiation. For those of you who are also in Physics 30, this is a little different version, not quite as much, even though you might recognize some of the questions from your previous bell work when you get there. Introduction to EMR, electromagnetic radiation. So this was right out of the textbook, and the idea is to show the sunlight coming down that light that you can see, that visible light, but we're going to see the spectrum. The electromagnetic radiation spectrum is a lot more than just light we can see. So it's 2.1 on your textbook if you're interested in checking it out. So EMR. EMR is light, both visible and light we cannot see. So it's the visible light and the invisible light. That's all around us. EMR light has both wave and particle properties. So we say that it transfers as a transverse wave. We'll see that in a bit. It has something called wave-particle duality. There was a long time where they fought over the idea, scientists fought over the idea whether it was a wave or if it was indeed a series of particles. There's two ways to transfer energy. Transfer energy as waves or transfer as particles. They knew light was transferring energy, but it behaves like a particle sometimes and a wave sometimes. We'll address what that is. It's these guys right here. So these photons, which are packets of pure energy, they have no mass. So it's like a particle that travels in a wave-like manner. So it's the position of these pure energy packets called photons that behaves like particles, but those particles are traveling as a wave. So I'm doing a wave-like motion with my hand right now. All EMR will be produced by accelerating charges. So what do we mean by that? Well, accelerating charges might be speeding up, slowing down, or changing direction. So if you have a charge that's stationary, nothing happens. It has a gravitational field around it, has a magnetic field around it, there's an electric field around it, but nothing else. A charge like an electron that's traveling at a constant speed, that'll have a magnetic field around it, but it will be a constant magnetic field. So there's no EMR from that. But as soon as you accelerate a charge by speeding it up, making it go faster, slowing it down, maybe stopping it, or changing its direction, by doing those things, then it gives off EMR. So we're going to see how that produces several different kinds of EMR, different ways, variations of that. Every time you have one charge, so if it's one electron speeding up, or one electron slowing down, or one electron changing direction, it will produce one photon of light. So these packets of light. So interestingly enough, it was Einstein who came up with the name photon. He was working on the work of a guy, a scientist by the name of Max Planck. And Planck first thought about the idea of photons, but he called them quanta. And quanta just simply means chunk of, a package of. And he did the math on it, but the math didn't work. So Einstein came in, stepped in, took Planck's work. He first of all made the math work on it, redefined it a little bit better, and changed the name to a photon. So EMR. EMR propagates by perpendicular electric fields and magnetic fields, with both changing. So here you have a device, it's a little spark gap, it's called, and it shoots electrons there, and back and forth, back and forth, back and forth. And so those accelerating charges, they start out from rest, they speed up, and then they hit the other side, and then they speed up, and they hit the other side. Those accelerating charges produce a spark, and they produce a vibrating polar molecule, but that will also produce a changing magnetic field. And the changing magnetic field here is shown in blue. Well, as soon as you have a changing magnetic field, it also then produces a changing electric field perpendicular to it. So then perpendicular to this red wave going up and down is that changing electric field, which is going to be changed by a constantly changing magnetic field. So then this changing electric field produces a new changing magnetic field. And then this changing magnetic field produces a new changing electric field, which produces a new changing magnetic field, and so on. And that's how light propagates. That's how it travels itself. Again, these are right angles, are perpendicular to each other, and they're also perpendicular to the direction of its traveling, as shown by a velocity vector here. And so one of the earliest forms of EMR that was ever found was a little spark gap like this, and they realized that there was something going on in terms of receiving that. So here's just a little bit better picture of that. Again, so it shows accelerating charges one of these charges accelerating by will produce one photon. So that packet of energy then is going to travel in a wave-like pattern because it's propelled by this changing magnetic field and this changing electric field. It's a little difficult to understand at first, but after you think about it, you talk about it, you read about it a little bit, it makes more sense. So the entire electromagnetic spectrum. So when we talk about light, we often just think of visible light, the Roy G. Biv, which is found right here in the green, just a very, very small section of the entire electromagnetic spectrum. So the longest of the waves are these radio waves. And this picture is a little bit counterintuitive in terms of showing this, but the longest kind of waves are radio waves, but they're also the lowest energy and the smallest frequency. So the frequency here, it says, is 10 to the 3. That means 1.0 times 10 to the 3. You move way to the other end, these magical gamma rays, they're going to be times 1.0 times 10 to the 23. So very, very high frequency, but very, very small waves. High frequency means high energy. So these are dangerous out here because of their high energy waves, very, very small. Over on this end, very long waves. These are up 10 to the 4 meters in this range, so that's going to be 10-kilometer range. So that's pretty darn long. Within radio waves, we also have television waves, and then into shortwave. Now this is, don't pay attention to the short waves. Next to those are going to be our microwaves. So the microwaves that are found in your microwave stove, also in your cell phone, they're going to also be fairly long waves, fairly small, quite a bit bigger than the radio waves and the far end, but and small energy. Next to that are the infrared. Infra means smaller energy, so it's referring to than red, so it's right next to the red. On the other end of violet, we have ultraviolet, which are bigger than violet in terms of energy and frequency. So infrared in here, we'll talk quite a bit about those when we get to the end of this PowerPoint. And then in the middle here, we've got the visible colors that we can see, the Roy G. Biv. I always said for years that indigo violet, they're both just purple. Sometimes people think of indigo as a dark blue. It doesn't actually really exist. It was just made up by Newton because he wanted to have 7 colors, because 7 was a magic number and he was really into numerology. So, but we stay with it because it makes it easy to remember, Roy G. Biv. And then next to it again, the ultraviolet. Ultraviolet are like black light. So if you go to West Edmonton Mall and you ride through Galaxy Land on that little train, you go through the tunnels and all the writing and those fluorescent things light up, or you see dandruff on yourself, or when you smile, your teeth are super bright. That's the ultraviolet that is picking up on that. Next to that, every time you go to the dentist, if you're a break a bone and have to go to the hospital, are the X-rays. And then last but not least are these very dangerous guys out here, the gamma rays. So we are going to talk about each of these different regions and how they're formed. You might be asked on a normal diploma exam, certain regions on here, but you're given the table in your green booklet. For today, I'm going to ask you a couple of questions in your bell work, like a particular EMR has frequency of 2.5 times 10 to the 21. What region will you think it would be in? Well, it's going to be times 10 to the 21. That's gamma rays. Might ask you about a frequency of 5.2 times 10 to the 5. That's going to be a radio. I might ask, right in here would be, between that would be 10 to the 10, be microwaves, and so on. Am I right? So you can expect something else to come back to this chart. So again, if you look at the radio waves, very, very long waves. Gamma side, very, very short waves. So from long to short, they go in this order. Radio, micro, infrared, visible, ultraviolet, X-rays, and gamma rays. The radio have very, very low frequency, and then if you go each level next to higher frequency, and then low energy on the radio end, high energy on the gamma side. So I might list 3 of these, any 3 of these, X-rays, infrared, radio. list them in order from longest waves to shortest, so then you would put them in that order. Or I might say it the other way, highest energy, highest frequency to lowest, so then you'd have to read them backwards. So let's start to talk about each type of. So radio waves. So radio waves we're very familiar with. We have an old-fashioned boom box like this. The radio antenna is going to pick up that radio signal and play it for you. My fire department radio that I bring to school every day, a couple of you folks are carrying those now as well. That sends an EMR signal. It's a light. It's radiation. It travels at the speed of light, 300,000 kilometers every second. 300,000 kilometers in a second. So if you key your radio and it goes like I'll do right here, the delay that you hear is actually the electronics. So that sent a signal up to the top of Grand, and then it sent it all the way to Grand Prairie, and it sent it all the way back down here as well. So radio waves produced when electrons accelerate back and forth in a linear antenna. So the linear antenna on the top of my fire department radio I just keyed, it sends the electrons up to the top, they stop, turn around, come back down, back and forth up that straight line. Whenever you have electrons changing like that in a straight line, it produces radio waves. Used for, in this case, fire department communication. The old blue boxes of the Centios we used to use for smart response system and for AM and FM radio stations. Microwaves. Microwaves, a lot more popular than just the popcorn makers that are in our house. They're the leftover warmer-uppers. So they're produced when electrons accelerate in a circular antenna. So they circulate by changing direction. They actually go at a constant speed. And this is the device that causes them to do that. So this is a little cyclotron that comes out of a microwave. And it'll send those around. A tiny one of those is in your cell phones as well. You know you're pretty cool if you have one of these old-fashioned rugby cell phones. So inside all of our cell phones, there's a little tiny cyclotron that's going to move electrons in a circle. And that's how the signal is sent. Used for cell phones, microwave ovens. In the old days when we used to have cable TV, microwaves would be sent that way. There's long stories I used to tell in class about those, but we're not going to get into those in this context. So microwaves are pretty important in our day lives. Infrared. So IR or infrared, a couple of things that are important about it. First of all, and we're going to see this for infrared, visible, and for ultraviolet. They're all produced the same ways. Electrons, they receive energy. Electrons jump up to a higher level in an atom. They can't stay there, so they drop down. When they drop back down, they give off a photon of EMR, a photon of infrared or visible or ultraviolet. So where do we see those? Well, first of all, if you remember grade 7 science, in grade 7 science, they told you that heat is transferred 3 ways: conduction, convection, and radiation. So when heat transfers as radiation, it's infrared. So you can see that where they keep burgers warm at McDonald's with the infrared lamps that they have. Those infrared lamps are also used for hatching chicks. But the other place very common is these TV remotes. So most TV remote controls are used an infrared signal. So the ones that I use to turn on my projectors, again, infrared. Now, if you're at home and you have a satellite receiver, some satellite receivers you have to be in the same room and point it right at it to make it change the channel. But some you can be around the corner, you can be in a different room. You can be in a different room, it's not infrared, then it's a radio signal, because the radio signals can actually penetrate the walls. But if you have to be in the room, have a line of sight, then it's the infrared remote controls. So infrared, again, infrared, that's how we transfer heat as radiation. So it becomes important, again, in the fire service. We have 2 buildings close together, one's on fire. We worry about that radiation, the infrared transferring over and starting the next house on fire, particularly if it has vinyl siding. So we have to protect those exposures. We even have a infrared curtain. So it's just basically a little hose that shoots up a little curtain of water that'll absorb that infrared and keep it from heating up the house next to it. Visible light. So here's your standard Roy G. Biv visible spectrum. produced when electrons drop down to a lower level. What do we use it for? Well, we read with it and other stuff that's important for visible light. And it's a wide range of different things it's used for. A lot of the burglar alarm systems still use the visible light range in terms of their sensors. Some go off into this ultraviolet range, though. So ultraviolet, UV, so produced when electrons drop down to lower levels again. They're used in black light. So this is an example of what they call a black light. Used to have them at the old discos and stuff. Some people actually use them. There's one of my neighbors up the street has some plants growing in his front yard, in his front window, and he has the black lights there to give the extremely high energy. There's ultraviolet around us all the time. We can't see it. But there is actually an old-fashioned thing from back in the 50s and 60s. It's called a bluing agent. You would add it to your clothes washer, and your white shirts then would seem to shine a lot better. All it was doing was leaving little particles that would reflect the black light that was for the ultraviolet that was around. Good goggles for skiing, for fighter pilots, especially when at high altitude. Sunglasses, good quality sunglasses, which nowadays are 90%, 99% of all, even drugstore sunglasses are UV screens. They block out that ultraviolet that can really damage your eyes, so the tinted glasses. So, interesting enough, so the glasses I happen to be wearing right now, when I go out into the sunlight, they tint. They're stimulated by the ultraviolet that's out there. So when I wear them inside my vehicle, they don't tint because the windows themselves filter out that ultraviolet that's coming. Now, there is some extremely dangerous, high-frequency, high-energy ultraviolet that comes off of the sun. Fortunately, that gets filtered out by our atmosphere. You'll see in some futuristic movies after long time atomic warfare and stuff where more of the ozone has been destroyed and everybody has to wear sunglasses or goggles outside all the time because the ultraviolet is that severe. Why do people wear sunscreen? It's not for the visible light, it's for the ultraviolet. It's ultraviolet that causes sunburns and possibly skin cancer. X-rays. We've all had X-rays at the dentist. If you've ever gone into the hospital with a suspected broken bone, they'll do some X-rays. Are X-rays dangerous? Yes, they are. But a few a year doesn't hurt you that much. The technicians that are doing them, they have to hide behind a LED screen all the time. So the dental hygienist, when she's doing it, she'll step behind the wall. That wall has a LED screen in it. The hospital, the tech there who's doing the X-rays, they have a screen, a physical screen that they actually step behind. How do you make them? Well, you actually make them by having electrons. You speed them up using charge plates. It gets electrons going super fast, and they hit a glass, in this case a metal target. They stop really, really quickly, and that gives off X-ray photons. So that's what we know about X-rays produced when high-speed electrons stop quickly and hit a metal or glass target. Check out your teeth, check out your broken bones, and stuff like that is what we use X-rays for. Gamma rays. So gamma rays are extremely dangerous. They're very, very high energy. If we had gamma rays bouncing around, we would all be crispy critters pretty quickly. They're extremely ionizing radiation, so they can damage healthy skin and healthy tissues and do some bad stuff. Where do they come from? Two places. First of all, they are one of the three types of radioactive decay. So in the next unit, we're going to learn all about radioactive decay. We're going to learn about alpha decay. We're going to learn about beta decay. And the third type is gamma decay. So sometimes when unstable nuclei decay into something else, so things happen. And one of the things that happens is it gives off gamma radiation, which can be very dangerous. The other way is when two antiparticles collide. So we're going to learn about something called a negative beta, which is just an electron, and a positive beta, which is called a positron. When those two particles steam towards each other and collide, they annihilate. So they're totally destroyed. They give off two photons of this gamma. All right, they do use some of this in nuclear medicine. Maybe you've heard about the gamma knife, where they direct a gamma beam specifically into a cancer area, and they take out cancer without having to actually cut into people. So it can be very, very beneficial. It has to be very carefully controlled. and it can be dangerous. It takes, quite a bit of shielding to protect yourself from gamma. So we're going to learn more about gamma later, and we'll learn about the other two types and how you can protect yourself from them when you have to work with them. Basically, the three factors that you do is number one, distance, stay away from them. Number two is shielding, have the right kinds of shields in between you and them. And number three is to limit your time of exposure. So we'll talk a lot more about that aspect, that as low as humanly possible later. So produced when some types of radioactive decay and by the collision of antiparticles. Extremely dangerous, protected by shielding, distance, and limiting time of exposure. The other aspect, or how are they used? They're used in some nuclear medicines for detection and for treatment of certain cancers. They're also used around here quite a bit in terms of highway development and in the drilling in oil and gas. So we have more trucks with radioactive material in them around northern Alberta than everywhere else in the world put together. So there's a lot of those sources. Each truck has a trained technician who knows just how to handle them and keep themselves and everybody safe. So that's it, folks. 21 minutes. Take care of yourselves. We will see you shortly.